In this lecture, I am going to present what is kinematic method and how to determine the plastic moment of a continuous beam by kinematic method. Then I would like to solve two problems on the continuous beam. Then coming to the analysis of a continuous beam by kinematic method. First, we should know what is kinematic method. Kinematic method is also known as mechanism or virtual work method. This method is based on kinematic or upper bound theorem, according to which a load computed on the basis of an assumed mechanism will always be greater than or at best equal to the true ultimate load. In this method, all possible mechanisms can be investigated and the one giving the least value may be considered as a real collapse load. Then we will discuss the analysis of continuous beam by kinematic method. In the case of a continuous beam subjected to transverse load, each span can form a collapse mechanism. So, in this case, the minimum number of collapse mechanism in the continuous beam is equal to the number of spans. A simultaneous collapse of all the spans constitutes a complete collapse of a continuous beam. So, in the case of continuous beam, if the working load and the load factor is given, the collapse load can be determined by collapse load is equal to working load into load factor. So, using this formula, you can determine the collapse load. If you know the working load of the continuous beam and the load factor, then you can find out what is the collapse load of the continuous beam. The plastic moment capacity of the beam is the higher value among all the collapse mechanism. This can be determined by equating the internal work done by plastic moment at plastic hinge to the external work done by loads. Then coming to the first problem, in the continuous beam shown in figure, plastic moment capacity of AB is to be kept twice that of BC. Determine plastic moment capacity of the beam. If the loads shown are working loads, take load factor as 1.5. So, this is the continuous beam, this is the two span continuous beam ABC, support A is fixed and support C is hinged, and span AB length 4 meter and span BC length 4 meter, and one eccentrical load is present at a distance 3 meter from the support A and 1 meter from the support B, and 40 kilonewton load is present. This load is given the working load, and on span BC there is having a concentrated load of 20 kilonewton at a midpoint of the span BC. This is also working load. So, here the load is given working load on the span AB and on the span BC. The plastic moment capacity of AB is to be kept twice that of BC. So, let us take the plastic moment capacity of BC is equal to MP and plastic moment capacity of AB is equal to 2 MP. Then, so the working load of the continuous beam is given. So, you can find out first the collapse load. The collapse load you can find out by multiplying the working load with the load factor, and the load factor is given 1.5. So, the collapse load is equal to working load into load factor, that is 1.5. And for this one, so what is the collapse load? 40 into 1.5, so this is equal to 60 kilonewton. For span BC, the 20 kilonewton load is present and this is working load. So, you can find out the collapse load. Collapse load is equal to 20 into 1.5, this is equal to 30 kilonewton. This is the figure indicate the continuous beam with collapse load. here you take the load, collapse load. This is 40 into 1.5 is equal to 60 kilonewton on span AB, and on span BC the load is 20 into 1.5 is equal to 30 kilonewton, and the plastic moment capacity of AB is equal to 2 MP and BC is equal to MP. This is the continuous beam with the collapse load. So here there are two span in the continuous beam, span AB and span BC. So there are two collapse mechanism. So first collapse mechanism is for the span AB and the second collapse mechanism is for the span BC. Here we have to find out the plastic moment from the collapse mechanism of AB and from the collapse mechanism of BC. Let us take the collapse mechanism of AB. So this is the collapse mechanism of AB. This is the load, collapse load 60 kilonewton, and let delta be the virtual displacement given to the hinge under the collapse load. This is equal to delta, and theta 1 and theta 2 be the rotations are the ends A and B. So at end A the rotation is theta 1 and at end B the rotation is theta 2, and this is the plastic hinge. So here there are three plastic hinge will be formed. So one plastic hinge are the fixed support A, and the second plastic hinge are the intermediate support B, and the third plastic hinge will form at the loading point. So three plastic hinge will be formed at A, B and under the loading point. Here given the plastic moment capacity of AB is equal to 2 MP and the plastic moment capacity of BC is given MP. You take the 2 MP at the plastic hinge at A, take 2 MP at the hinge under the load, and at B take the plastic moment is equal to MP, because at joint B, so this side on span AB the plastic moment capacity is 2 MP and on span BC the plastic moment capacity is MP. So here you take the lowest plastic moment at the joint B, and at A you take the plastic moment 2 MP, and under the load at the plastic hinge you take the plastic moment 2 MP. So this is the 3 hinge and this is the plastic moment capacity of the 3 hinge. Then find out the internal work done. So by considering the collapse mechanism of span AB and find out what is the internal work done. So here the internal work done you can find out by multiplying the plastic moment capacity of the hinge and the rotation. So here at A the plastic moment capacity is 2 MP and the rotation takes place theta 1. So the internal work done is equal to 2 MP into theta 1, 2 MP into theta 1. And then under load the total rotation takes place theta 1 plus theta 2 and the plastic moment capacity of this hinge is 2 MP. So the internal work done here is equal to 2 MP into theta 1 plus theta 2, and at the plastic hinge B the plastic moment capacity is MP and the rotation takes place theta 2. The internal work done due to this hinge is equal to MP into theta 2. The internal work done due to all the hinge equal to 2 MP into theta 1 plus 2 MP into theta 1 plus theta 2 plus MP into theta 2. But we know from this figure, so this is the virtual displacement and this length is equal to, from this to this is 3 meter and from this to this is 1 meter. This 3 into theta 1 is equal to delta is equal to 1 into theta 2. 3 into theta 1 is equal to delta is equal to 1 into theta 2. Then after simplification theta 2 is equal to 3 theta 1. This is equation 1. So here you put the theta 2 value. Then after putting the theta 2 value, the internal work done is equal to 2 MP theta 1 plus 2 MP theta 1 plus 3 theta 1. Theta 2 is equal to 3 theta 1. 3 theta 1 plus MP into 3 theta 1. Then after simplification, the internal work done is equal to 13 MP into theta 1. Then determine the external work done. So on the span AB, the collapse load 60 kilonewton, and you can find out the external work done from the collapse load and the virtual displacement. The multiplication of the collapse load and the virtual displacement will give the external work done. So the external work done is equal to 60 into delta. So here the external work done is equal to 60 into delta. But we know 3 theta 1 is equal to delta is equal to 1 into theta 2. Then after putting the delta here, delta is equal to 3 theta 1 here. The external work done is equal to 60 into 3 theta 1. So here you know what is internal work done and what is external work done. Then after equating the internal work done is equal to external work done, then you can find out what is the plastic moment. Internal work done is equal to 13 mp theta 1 and the external work done is equal to 60 into 3 theta 1. Then after simplification of this equation, the plastic moment is equal to 13.846 kilonewton meter. So this is the plastic moment you got from the mechanism of span AB. From the collapse mechanism of AB, you got here the plastic moment. This is equal to 13.846 kilonewton meter. Then take the collapse mechanism of BC. So this is the collapse mechanism of BC. So here this is the span BC, and here this side is simply supported, intermediate support. So one hinge will be found at B, and the second hinge will be found under the load. But here this end is simply supported, so here the moment is 0. So here there is no hinge, only two hinge will be found. One hinge is at A, second hinge will be found under the loading point. So this is the collapse mechanism. So here this is one hinge and this is another hinge, and here there is no hinge, and this is the 2 meter and this is 2 meter. Here also let the virtual displacement delta be given under the loading 30 kilonewton, and theta is the angle at B and C. Due to the concentric loading, the angle at both ends are equal, that is theta at B and theta at C, and under the loading the rotation takes place theta plus theta, 2 theta. Here also you have to find out what is the internal work done at B and what is the internal work done under the loading by multiplying the plastic moment and the rotation. At a plastic hinge B, the internal work done is equal to mp into theta, and under the loading the internal work done is equal to mp into 2 theta. Then the total internal work done is equal to mp into theta plus mp into theta plus theta. This is equal to 3 mp theta. This is the internal work done from the collapse mechanism of BC. Then find out what is the external work done. So here the load is present 30 kilonewton collapse load, and this is the virtual displacement. So you can find out the external work done by multiplying the collapse load with the virtual displacement. So the external work done is equal to 30 into delta. This is the collapse load and this is the virtual displacement. But we know 2 into theta is equal to delta. 2 into theta is equal to delta. So here you put the value of delta. Then after putting the value of delta, the external work done is equal to 30 into 2 theta. Then equate internal work done with the external work done. Here you know the internal work done is equal to 3 mp theta, and the external work done is equal to 30 into 2 theta. Then after simplification, the plastic moment is equal to 20 kilonewton meter. The collapse mechanism of AB, here you know the plastic moment capacity is 13.846 kilonewton meter. And from the collapse mechanism of BC, so here you got the plastic moment is equal to 20 kilonewton meter. The plastic moment is the higher value among the two plastic moment of span AB and span BC. So the plastic moment capacity is equal to 20 kilonewton meter, and the plastic moment capacity of AB is equal to 2 MP. But you know the plastic moment capacity of AB, you know the plastic moment capacity of AB is equal to 2 MP, and plastic moment capacity of BC is equal to MP. So here you got MP is equal to 20 kilonewton meter. The higher value you are choosing the plastic moment of the continuous beam. So MP is equal to 20 kilonewton meter, and for span AB the plastic moment capacity is equal to 2 MP. So this is equal to 2 into 20, 40 kilonewton meter. So this is for span AB the plastic moment capacity, and the plastic moment capacity of span BC is equal to 20 kilonewton meter. Then coming to the second problem, calculate the plastic moment capacity required for the continuous beam with working loads shown in figure. Take load factor is equal to 1.5. So this is the continuous beam, two span continuous beam with the support A is hinged and support C is roller support, and this is the intermediate roller support, and the span AB length 4 meter and span BC length 6 meter, and the plastic moment of span AB is given MP, and plastic moment of span BC is given 2 MP, and one concentrative loading 40 kilonewton which is present midpoint of span AB, and the uniform distributed load of intensity 20 kilonewton by meter which is present throughout the span BC. So here also this is the working load is given on the continuous beam. So this is 40 kilonewton and this is 20 kilonewton per meter. So first you find out what is the collapse load. The collapse load is equal to 40 into 1.5, this is equal to 60 kilonewton, and here the collapse load is equal to 20 into 1.5 is equal to 30 kilonewton by meter, because the load factor is given 1.5. So this is the figure which shows the continuous beam with the collapse load. This is the collapse load, 40 into 1.5 is equal to 60 kilonewton. This is 20 into 1.5 is equal to 30 kilonewton by meter. Here also you have to go for two mechanism. First mechanism for the span AB and second mechanism for span BC. First start with the mechanism of span AB. So here you see the end A is simply supported. Here the moment is 0. Here there is no plastic hinge, and here two hinge will be formed. One hinge at the support B and another hinge under the load. Under the load one hinge will be formed, and at the support B one hinge will be formed. Let delta be the virtual displacement given under the loading 60 kilonewton, and let theta is the rotation at the end A and B. Here the load is present at the midpoint of the span AB, so the rotation at end A and B are equal, and this is equal to theta, and the rotation at the loading point is equal to 2 theta. Here the plastic moment is given for span AB MP and for span BC 2 MP. So here under the loading 60 kilonewton the plastic moment is MP. At the plastic hinge B the plastic moment is, you have to take MP, because this side MP and this side 2 MP. So you have to take the minimum plastic moment at the intermediate support. Here the plastic moment is equal to MP and MP. Then find out what is the internal work done. This is the collapse mechanism of AB. Then find out the internal work done. So here there is no hinge, so here the internal work done is equal to 0, and here there is hinge, so here the internal work done is equal to mp into 2 theta, and here there is one hinge, the internal work done is equal to mp into theta. So the total internal work done is equal to mp into theta plus mp into 2 theta. This is equal to 3 mp theta. Then find out the external work done. So here this is the collapse load and this is the virtual displacement. So the external work done you can find out by multiplying the collapse load with the virtual displacement. So the external work done is equal to 60 into delta. The external work done is equal to 60 into delta. What you know, delta is equal to 2 into theta. You have to put here delta is equal to 2 into theta. Hence the external work done is equal to 60 into 2 theta. This is equal to 120 theta. Then after equating the internal work done and the external work done, so you can find out what is the plastic moment. So the internal work done you got here 3 mp theta, and the external work done you got here 120 theta. Then by equating the internal work done and the external work done, 3 mp theta is equal to 120 theta. Then the mp is equal to 40 kilonewton meter. This is equation 1. Then coming to the mechanism of span BC. So in span BC, so this is here having the uniform distributed load UDL of intensity 30 kilonewton by meter, and this is the end support C. So here there is no plastic hinge, and at the intermediate support B there is one plastic hinge. Another plastic hinge will be formed between B and C at the maximum bending moment section. So this is the collapse mechanism of span BC. So here this is B1 hinge, at the maximum bending moment another hinge, and the maximum bending moment that will be occurs at a distance 0.414 L from the support C. Already we have discussed in the previous lecture where we will get the maximum bending moment in the case of prop to cantilever with UDL. So here also this span is also you have to consider as a prop to cantilever. This end is fixed and this end is propped. Here the maximum bending moment will occur at a distance 0.414 L from the support C. The mechanism is formed when section yields at B and at another point in the portion BC. Yield at B and another point on the span BC. Let plastic moment at B is equal to mp. Since bending moment diagram in span BC is similar to that of a prop to cantilever with a parabolic variation for free moment and end moment mp at one end and 0 at the other end. This side the plastic moment is mp and this side is 0, and parabolic variation for the free moment. Already we have discussed in the last lecture. Hinge will be formed at point of maximum positive moment, which is at 0.414 L from simply supported and C. So at a distance 0.414 L from the C. So here the hinge will be formed, and this is the maximum positive moment section. This is the maximum positive moment section. Let delta is the virtual displacement we given at the maximum positive moment section. Theta 1 and theta 2 is the rotation at the end B and C. Plastic hinge under the maximum bending moment, the rotation is theta 1 plus theta 2, and at B the rotation is theta 1 and at C the rotation is theta 2. So first find out what is the internal work done due to the plastic moment and the rotation. At joint B you have to take the plastic moment mp, because this side mp and this side 2 mp. So here you have to take the minimum plastic moment mp at the point of maximum positive moment, and here for this plastic hinge you take the plastic moment equal to 2 mp. Find out what is the internal work done. So internal work done at the plastic hinge B is equal to mp into theta 1 At this hinge, the internal work done is equal to 2 MP into theta 1 plus theta 2, but here there is no hinge, so the internal work done is equal to 0. Then what is the total internal work done? The total internal work done is equal to MP into theta 1 plus 2 MP into theta 1 plus theta 2. MP into theta 1 plus 2 MP into theta 1 plus theta 2. Here you find out what is the relation between the delta and theta 1 and theta 2. So here this length is 0.586 L and this is theta 1. So 0.586 L into theta 1 is equal to delta is equal to 0.414 L into theta 2. From this relation you get theta 2 is equal to 0.586 by 0.414 theta 1 is equal to 1.415 theta 1. Then put the value of theta 2 in this equation here. Then internal work done is equal to MP into theta 1 plus 2 MP theta 1 plus 1.415 theta 1. Then internal work done is equal to 5.83 MP into theta 1. Then find out the external work done. The external work done is equal to total load into average distance moved. So using this formula you can find out the external work done. So here you see the total load is equal to 30 into 6. The total load 30. So here the collapse load is given 30 kilonewton by meter and the total length is 6 meter. The total load is equal to 30 into 6 and the average distance moved. So here this is the virtual displacement delta and the average virtual displacement is equal to delta by 2. So the external work done is equal to total load 30 into 6 and average distance moved, this is equal to delta by 2. Then you know delta is equal to 0.586 L into theta 1. Delta is equal to 0.586 into L into theta 1. Then put the value of delta here. Then after putting the delta value, the external work done is equal to 30 into 6 into 1 by 2 into 0.586 into 6 theta 1. Then the external work done is equal to 316.44 into theta 1. So this is the external work done for span BC. And here you got internal work done for span BC 5.83 MP theta 1 and the external work done for span BC 316.44 theta 1. Then after equating the internal work done with the external work done, so you get what is the plastic moment capacity. So 5.83 MP theta 1 is equal to 316.44 theta 1. Then MP is equal to 54.28 kilonewton meter. So this is the plastic moment capacity from the span BC and this is the plastic moment from the span AB. From the span AB the plastic moment is 40 kilonewton meter and from the span BC the plastic moment is equal to 54.28 kilonewton meter. From the mechanism AB, MP is equal to 40 kilonewton meter and from the mechanism BC, MP is equal to 54.28 kilonewton meter. Hence, a plastic moment capacity is taken as the higher value of both the mechanisms. So you have to take MP is equal to 54.28 kilonewton meter. Then you can find out what is the plastic moment capacity of AB and plastic moment capacity of BC. So plastic moment capacity of AB is equal to MP and plastic moment capacity of BC is equal to 2 MP. So the plastic moment capacity of AB is equal to MP is equal to 54.28 kilonewton meter and plastic moment capacity of BC is equal to 2 MP is equal to 2 into 54.28 kilonewton meter. This is equal to 108.56 kilonewton meter. So this is the all about the analysis of the continuous beam when the working load is present. So you can find out first the collapse load by multiplying with the load factor. Then you have to find out the plastic moment by equating the internal work done with the external work done. Then after getting the plastic moment from each mechanism, you have to consider the higher value of the plastic moment. Then you can find out what is the plastic moment capacity of each span. Now all are clear.